Okay, so this is lesson 2 of carboxylic acids and their derivatives, and we are looking at esters and the uses of esters. So when esters were first discovered in the 50s and 60s and started to be used, they were mainly used as perfumes and fruit flavorings. So we have a nice picture of Wrigley's delicious juicy fruit, which contained 3-methyl-but-1-yle ethanoate. So 3-methyl-but-1-yle ethanoate, that molecule there. Yeah, I'm sure it was delicious. Nowadays, we tend to use fruit extracts, which are slightly more reassuring. But esters are used as solvents. So the ethyl ethanoate is sometimes used as a glue solvent. It's also used as nail polish remover. Perfumes are often found containing esters. If you look at the back of any perfume bottle, there'll be a list of all sorts of compounds. You'll often see the telltale 08 in the list, as well as lots of other names and numbers and fantastical things. Plasticizers. So a plasticizer is a molecule that's added to a plastic to keep it springy. If you want your plastic to be, it's not particularly flexible. If you want your plastic to be flexible, this is a ruler. There we go. If you want a plastic to be flexible, and you just make the plastic as it is, the long polymer chains get close together, and the strong intermolecular forces tends to make it rather rigid, which is sometimes what you want. Sometimes you want rigid plastic. Think about some of the plastic containers you have at home. Some of them are quite hard and solid. But if you add these large plasticizer molecules, then they keep the polymer chains a little bit apart from one another, and that weakens the intermolecular forces and makes the plastic a little bit more flexible. When we talk about PVC windows, PVC is of course polyvinyl chloride, which was the old name for polychloroethene. So if I draw chloroethene and as a repeating unit, that will be the monomer that's repeated. That's PVC. So PVC windows have to be hard and rigid. You obviously don't want your windows to be kind of loose and floppy. The glass would just fall out. So you'll sometimes see the letter U put in front of that. That means unplasticized. It's PVC without a plasticizer. We'll do more on polymers later on. But the specific type of plastics that specific type of esters I want to talk about today are the esters that come from fatty acids. So at this point, the biologists in the room will all be nodding their heads sagely and going, "Ah, yes, I know all about that." Okay, that's good. You should know all about that. Let's start off with a molecule that's probably familiar to biologists as glycerol, but for chemists it's going to require an IUPAC name. If you could just pause your video and come up with the IUPAC name for that molecule, please. So 3 carbons, so it's prop something. We've got 3 alcohols, so it's going to be a triol. So I'm just going to, I can't work the name out like that. It's going to be triol, so prop and triol. The 3 alcohols are on 3 different carbons, so 1 2, 3, carbon 1, carbon 2, carbon 3. So propan 1, 2, 3 triol, but we remember that if there's ever a di, can't quite see there, it's out of shot, but remember 007 says di has an E in it. We have to remember to add the E in the root name of the carbon chain. Same for this. So for tri, I know tri doesn't have an E in it, but it does kind of. Propane, did that make any sense? Propane 1, 2, 3 triol. Okay. If I react that with 3 molecules of a carboxylic acid, what would that produce in the way of an ester? Pause the video and have a go at drawing the ester or triester that we would make from that. So each of the acid groups is going to react with an alcohol group and form a new ester group. Remember, this is the alcohol end, O, CO, and then we'll make that. Don't worry, you don't need to name that, but what we've made there is a triester, and of course I could use different carboxylic acids and I could have different ends on here, so that's why I've put an R group on the slide there. R could be anything, right? It could be all sorts of big funky molecules. Well, there are some very big and very funky molecules out there, and they're called fatty acids. And fatty acids are any molecule where we've got, you know, a big long carbon chain. So I might have, I'm just making this up, I might have, say, 15 carbons or 16 carbons in that chain, and then the acid group on the end. And if I reacted that with my glycerol, well then the molecule has to kind of flip around, doesn't it? I would put that on here, so that would become CO, CH2, 15, CH3. Okay, does that make sense? And if I do that to all of them, so CO, maybe this one's a different molecule, let's make that a 17, and let's make this one a 19. So we've got some different fatty acids there that have joined onto our glycerol. That is no longer glycerol. We've now made our triglyceride. So triglyceride is a triester made from 3 fatty acids reacting with glycerol. Okay. I just pulled that off the internet there. Now, just before we get on to the next bit, it's the interesting bit, just a word about saturated and unsaturated fats. Sorry, did I mention that's a fat? A fat or an oil, sorry, for those of us that don't speak biology. The triglyceride molecule is the basic molecule of fats and oils that are found in nature and found in your body and so on. And fats and oils can, of course, be saturated or unsaturated. And you've probably seen these words bandied around. They're used in food labelling, no saturated fats, and so on. And they mean the same thing as they mean in chemistry. Saturated means no carbon-carbon double bonds, and unsaturated means contains carbon-carbon double bonds. Polyunsaturated means contains lots of carbon-carbon double bonds. And we tend to think of the unsaturated fats, which come from vegetable oils like olive oil, sunflower oil, and so on, as the more healthy oils, whereas the saturated fats that come from animals, so butter, cheese, meat, they're the less healthful ones. We talk about cholesterol as well. These saturated fats tend to form layers of plaque in your arteries, and that slows blood flow, and then eventually the blood can't get to your heart, and then you have a heart attack and die. It just depends whether there's carbon-carbon double bonds in the molecule there. So the fat molecules are also quite useful to us in chemistry, because we can break them back down into their constituent fatty acids and glycerol. So if I wanted to break that molecule down, I have to break those ester groups. And if you think about how the molecule was made, it was made from glycerol and the fatty acid molecules. So I go backwards in the other direction. I'm breaking those bonds where the esters originally formed around here. If we're breaking a bond and we're using a process that involves water or a solution of water like hydrochloric acid, then that's called hydrolysis. So breaking bonds using an aqueous solution. Now it's quite hard to break down a fat molecule. I'd have to boil my fat up with concentrated alkali. Usually works best rather than concentrated acid. So I could boil this up with my concentrated alkali for several hours. It's a slow process, and it would break it down into the original fats and glycerol. So let me just draw that out. So we're going to break this down. I haven't left myself much room, have I? But we get the original glycerol. Let's just pop that up there. So this is sodium hydroxide we're using. So I'm going to break it down into glycerol, or propane 1,2,3 triol, if you like, and then the fatty acids. Except, let's just use the first one, the 15. Except when the fatty acids break off the glycerol in the presence of sodium hydroxide, acid plus base, they're going to come out as salts. So hydrolysis of my ester will produce the original alcohol, whatever it is, glycerol in this case, and the sodium salts of the fatty acids. These are the important ones to keep your eye on. Why? Well, about 150 years ago, a cunning young man from the part of the country called Port Sunlight came up with a method of rendering, it was called, fat molecules into glycerol and salts of the fatty acids. And made soap. That was Sunlight soap, which was first produced in Port Sunlight, and was the beginning of the Lever Corporation. Okay, I'm just going to wipe all of this. And focus in on the soap. So a soap molecule, it's not very clear there, but let's draw a skeletal formula. So we've got 16 carbons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I did not leave myself enough room. 16 carbons, then the COO, and then the charged end. So what do we know about long carbon chains? Think petrol, think diesel oil. Well, long carbon chains, long chains of hydrocarbons are not soluble in water because they are non-polar. So we've got a long non-polar tail here, which would be insoluble in water, but soluble in other non-polar substances like fats. And on the other end, we've got this, the sort of the head end of the molecule, which is polar, and polar substances like salts, sodium chloride, are very soluble in water. Insoluble, obviously, in fats and oils. So we have an interesting molecule here, our soap molecule, which can mingle both with fats and oils on one end and water on the other end. So, therefore, acts as a mechanism for taking fats and oils and mixing them or dissolving them in water. So let's say I'm washing something and I've got a big blob of oil on my clothes. It won't wash away in just plain water because it won't mix, it won't dissolve with plain water. But along come my soap molecules, and the soap molecules have long non-polar tails which will mingle with the oil. Of course, they've also got heads on. The heads will stick out though, so I'll end up with a molecule, a blob of oil that gets surrounded by these other molecules, and therefore enables the oil, so we've got water out here, enables the oil to dissolve in water. So we call this an emulsifier. An emulsifier is any molecule which enables two things that don't normally mix, oil and water, to mix, to dissolve. If you're making salad dressing and you mix oil and vinegar together, they don't mix very well, they'll separate out. If you add a bit of egg yolk, then the oil and the vinegar will mix, you make mayonnaise. So in that case, the egg yolk is the emulsifier. So our soap molecule is an emulsifier, enabling the oil to mix with the water, so hence soap enables you to wash your clothes, wash your face, wash your hair, etc. One last thing, I think. I don't know how familiar you are with Tyler Durden, but if you've not seen Fight Club, they have a scene in it in which they take fat and render it to make soap. What I like about Fight Club is they get the chemistry right. They get the fat, they get hold of some fat. I won't spoil it as to where they get the fat from. They render it with what they call in the film, they call lye, but that's just another name for concentrated sodium hydroxide. So they render the fat, it's another name for hydrolysis. They render the fat with lye, and they make soap. But what they're really after is the other byproduct, the leftover glycerol. Why do they want to make glycerol? Because if you take glycerol and you mix it with concentrated nitric acid and concentrated sulfuric acid, then it replaces the H's on the end and makes nitro groups on the end. And now we have tri-nitrosyl nitroglycerine, which is not stuff you want to mess around with. It's a high explosive. Mix a little trinitroglycerine with an old traditional method, mixing it with some clay called kieselguhr, and you'll make dynamite. There we are. Interesting and informative. See you soon.